Okay, for the last time, we modeled this. So I taught you the basic fundamentals of SAP 2000, how to model the local axis and how to read the output. So I sent you some of the reference videos to uh, learn how to read the output of shell element or whatever area element, right? Especially, and this time, yeah, it has been run. So we saw like the model case. So you learned yesterday about the model analysis of the structures, right? So whatever the flows they, how much flows they have, right? They can be idealized into lump mass models, right? In which you can analyze how many modes, their periods, and the same thing is done here. If you go to the deformations, let me see. Yeah, if you go to deformation, you can run model analysis, and yeah, this will show you the mode 1, right? Mode 1, the T is around 4.0 and frequency. So if you start animation, right? So the first mode is a twisting mode, right? It has some torsion. So I told you we prefer the buildings which are non-twisting, right? So at the initial design stage, we arrange the so you will see, except for the shear wall or the lift wall, the building is symmetric, so that it should be non-twisting. But with the shear wall, it is now twisting, right? So we have to arrange those shear walls in such a manner that building should be non-twisting, right? So what we are going today, so the first mode is twisting mode. So you will see the second mode, yeah, it is a translation mode along x direction, right? So likewise, you know how what are the models and other things, and from display options you can take the outputs as a structure output, the model information, model mass participation ratios, and the frequencies. Everything is there. So you just need to click it. Yeah, everything here. Periods and everything there. I think I didn't go to tables. Mass participation ratio. Yeah, sit here. So you'll see the mass participation ratios. Okay, UX direction, UI, UZ, right? So yeah, we'll do the model. We'll open a new model. So I will not be using grids. So I will just go to 3D frames, right? So I need a frame where the number of story is 1, okay, and number of bays is 4 in x direction and y direction 4. Story height is 3.6 meters. So my units are kilonewtons and meter. So bay within x direction is 7.5 meters, and in y direction it's 6 meters. So if I want, I can define the sections also here, but I will just use it, right? So I have the frame, right? And I will go and define the materials. So that's the first thing to do. So add a copy of this material. So I will choose this as grade 30, right? Grade 30. So you will notice, yeah, this is 25, right? When I add this the following will be automatically updated, the mass per unit volume. So modulus of elasticity is 27 GPa. So that means yeah, it is correct. And Poisson's ratio 0.15. Yeah, it's better. Yeah, now it's done. So if you need several concrete grades, so you can define it here, apply for different materials. That doesn't matter, right? So if you want, you can later change the materials then. So, and also I should, yeah, I will do it later. So yeah, some of the materials also I have. So I need to define, sorry, sections, frame sections, add new property, it's concrete. So I need a beam which is 600 depth and 400 width, right? 600 and 400. So the material is, sorry, I think I didn't save the material. Let me see. Yeah. 30, 25. So go to modify. You can select the material grade 30. Okay. So it's done, right? So if you want, if I want, I can define another one for the columns. Columns I will use, it's 30-story building. So the upper 50, sorry, lower 15 will be 1000 columns, right? So it's 1 meter, 1 meter. So I'll make another. So for the upper 30, so I will use a column of 800, so which is a square section, 8 and 8. It's done. So, and I will make some additional beams as well. Okay. So I'm not gonna spend much time on modeling because I already taught you from the basics the last time, right? So add beam, and so I will show you why I need this. Okay, add beam, and then add coupling beam. Also I will select yeah, 0.21. That's okay, and other things are okay, right? So I can go to define an area section. So slab, I can use slab 200. So yeah, the thickness is 200. 30 shell thin, it's a shell thin. Okay, so I can add a copy of this section, and that is slab 175 millimeters. So that's 0.175 and 0.175, right? So grade 30. Yeah, that's done. And I can make another one for shear walls. Shear wall 250. 250. That's also shell thin. If you want, you can use it as membrane, because then the results will be conservative, as these cell sections will not absorb any flexion, right? And for later I will use for pile caps. And if you want to model transfer plate, so that's also shell thick. The pile cap also shell thick, so I will define some the pile caps. So that is shell thick. It's around 1.8 meters thick. Okay, so you can define another grade from here. You already have, right? So this is my walling arrangement. This is going to be like, so I have the frame here. So I'm in XY plane at Z equals 3.6 meters. So I will use these two. First, I need to divide these frames. So I will use this one. So I will replicate it from x 2.5 meters, number of times 2. Okay. So, and I will use this replicate minus 3.6 times 1. So this is how I'm going to use the so these things should be divided from the sections where they connected, right? Edit lines. So you can go to edit lines, divide frames. So break at intersections, right? Now you can do it. And also you need to, replicate 0, 3. Okay. I think that's done. So these are the places where I get the walls. That's why I divided using lines, right? So I can use these for define the walls, right? Lift doors. Okay. So these are the places, and this is shear wall also, right? So for this arrangement, I will later come to the reason. So keep it in mind. I didn't tell you the reason still. Okay. So lift all here. So here many people can gather. So I will use a slab thickness of 200 here, and elsewhere everywhere is 175 the slab is, right? So in this case I will model the slab, okay, but there's a specific way to do it, so I'll show you how, right? So yeah, so I'm going to extrude the walls, right? So you can use the extrude option, you don't need to draw any line elements further. So I showed you last time how to do it. So I will use extrude line to areas, right? So it's 0 minus, you can select minus 3.6. The all is, this is shear wall. Yeah, you can use that for lift wall as well. The number of times 1. So the walls are connected. Now it's done, right? So I'd like to have these beams. The reason is if you have these beams, you can transfer these loads to this wall very well, right? Rather than connected by using a area elements. So from the finite elements, if you have the area elements, that's only connected at 4 nodes, right? If you want to connect it at each location, what you have to do is simply mesh it, because how you mesh from the point where you mesh, they define the matrix, right? So if you define it from place to place, so it know the data uh, where the model can be analyzed, right? So in such case, so I'm not going to mesh it, right? So the reason is, if I reason can be seen in later, I will show you within 2-3 minutes. So these beams, okay, these beams I would like to have some small beam, right? So I would have it, I would assign frame sections. So this additional beam, this one, okay. So this is the additional beam. So this one is additional coupling beam. The players used to join these beams, but it's still also the same section, okay. We can define a section later depending on the coupling action, which we'll be learning in the next lecture, right? So these are additional coupling beam. So other beams you can so this is also, this is also a additional beam. Assign frame section. Yes, now you don't need this beam because we only to divide the sections. Okay, so yeah. So I will use, so I will assign the beam frame. Okay, so now it's done. So the beams are done, right? So this one is additional beam. Okay, so one thing you need to do is, now I have the wall, so I don't need these columns, right? So these 4 columns, when you click it, you will see the dotted line is selected, so that is the column. But if it is selected like this is the wall, right? Don't delete it. So I can delete the columns, but these places should have a support, right? So you can select those points, right? And assign a pin support. Yeah, now it's done. Okay, so yeah, it's done. So I think I selected the beams. Okay, so I will go to 3D view and XZ plane. So I'll set the aperture to 0. So now I can select the every columns. So don't worry if you selected shear force, because you are only assigning it to a frame column, right? So now it's done. Yeah. So everywhere has been supported, right? So now I can go with loading, right? So the last time, right? Last time I did not draw the slab, right? This time I'm going to draw, and for a reason, right? So first I will add the loads, right? First I will add the loads. So it is not a big deal, so I show how to do it. So line by 45, right? So this is 3 7.5 6. So the half is 3 meters. So the UDL is 3 meters high if you add a unit load. So in particular case, you have to draw like this. So I will define load pattern. So this is dead, that's okay. Then I have the unit load 1 for So in this case, I have different slab systems, right? Different slab thicknesses. So I will use 2 unit loads. In such case, you have to use, right? If you have different slab thicknesses, or if you have the loads difference of the acting on the slab, right? In that case, you have to use different slab thicknesses. So add new load pattern. So then the UL2 also add new load patterns and wind in X direction. So I will add that as wind. So you will see auto load patterns are there. You don't need to add manually. You can do it using this, but I will use manually, right? You have to know how you're going to add automatic wind loads, right? So now everything's done. Unit loads done. Even the earthquake loading are there, right? Snow loading, everything's there. So you can go ahead and yeah, add the loading. So last time I told you how to add it, right? So if you have some beam, right? So these beams, so you can add distributed load. So all these beams are 7.5 meters. So I will take the absolute distance for about 3 meters. It will have the load 3, and for up to 4.5 meters that will have also 3, and up to 7.5 meters that will be 0, right? So you will use unit load 1 and replace existing. Everything's done, right? So for the interior beam, so you'll have to add it twice, right? So you know the reason, right? Distributed. So I have to add to existing, right? That's done. So in the other way around also, you have to add the loads. So that's a triangular distribution, right? That's a triangular distribution where you need to add. So it's also UL1, okay? So that is only 6 meters, right? So 0, 0, and here it's 3, right? So yeah, that's done. So yeah, I think it's done. So you can again select the interiors. Right. These will have different loading because it is divided, right? You can't select it as because it's the length is not the same as earlier. So I can edit. Now I have the loading 6, 6 everywhere. So for this one, I will use a yeah, I can use yeah, I will use something like this. A triangular load up to the 50% of this beam, and then 6 and 6 here and then here. So likewise I will use, and this panel has a different loading system. I will arrange for these two beams, right? A unit load 2. So this look like a one-way slab, so you can use a line load, right? Distributed and line load from UL2, right? So the slab is around 2.5 into 6 meters. So that you will, if you add a 1 unit load, so you will see the height of each UDL is 1.25, which is 2.5 over 2, right? So likewise, you can use other things. You can use a triangular load, right? Otherwise, you can use a triangular load. So I will show you the loads which right? I will save it. So I will open this one. I think the same thing I modeled last time also. I will open it. Yeah, there's no loading. So I'll go to our model. So you have to apply loads also, right? So since this is a triangular like one, so you can add a triangular load to this beam, look like something similar to this one, right? And this beam is not loaded. This beam is not loaded. That's a middle all of this lift. So only these walls will be loaded in a not two times, only one time, right? From these panels, from these panel, from these panel, from these panel, right? That's only, right? And this one, right? So this has a different loading arrangement as I shown you, right? So you can apply everything. So once you apply everything, you can draw the slabs, right? You can draw the slabs. So I will use a slab 175. So enter it. Enter. Right. So here you have a 200 millimeter slab, right? Yes. So if you want, you can just extrude the section and view. So here you can see fill objects and extrude. So you will see the slab, everything is there. And yeah. So it's done. So the problem is, okay, now you will see the sections also. So it is everything is, this is small beam which is connecting this for the load transfer. So I will not load the slab because you know these quadrilateral element, right? Four noded element is connected only at these four locations. So that's the finite element, right? So if you need to increase the load transfer, you need to mesh it so that these points also will be connected to the slab, and more you mesh it, it will though you so the results will be accurate, right? So the problem is if you mesh this one, right, so you will mesh all of these panels, let's say around 0.25 0.3 intervals, okay? So that is a fairly good mesh, right? So you use small 0.3 by 0.3 squares to mesh it, and imagine you will have many small elements within the slab, and when you multiply with the number of stories, right, so you will have large number of meshed elements, right? So your computational time will be much larger, right? If you have a good computer, that's okay, but that's not needed for that, right? So we have already distributed the loads to the beams, right? So we don't need the slab to transfer the loads, but the problem is slab should have now the mass, as you already know the model mass, right? So at the floor level, they should count the mass of the slab, right? So here's what we are doing the trick. So here's how we are doing the trick, right? So you need to define a separate material for the slab, right? So what I'm going to do is, right, you need to define a material which is grid 20. I will add a copy of this material, slab weightless. Okay, so when you update it here, right, so you will see this will be automatically updated. So I need to go to advanced properties, right? So I will go to advanced properties. So here you can edit everything, so it will not be updated. So I will use 0.001 and I will keep it as it is, because the mass and weights are different. Weights are for the loads, right? Mass is needed for the model analysis, right? So the slab has a mass, but the weight is not there, so it will not transfer any load. But when you define the mass, so for the model analysis, model will calculate its mass. It's there, not the weight. No loads will be transferred, so that weight per unit volume is almost zero, but the mass is there, so that model can still calculate its mass. So that mass should be needed to calculate its natural frequency. As you know, right, it's k over m. So the model can calculate its mass, right? So, and what you can do here is right, yeah, it's done. So click OK. So this is slab unit less, right? Sorry, weightless. Weightless. And click OK. Click OK. You need to yeah, what you need to do is go to slab properties, right? So slab and modify, and you only need to change the right. You can use this one, slab weightless, and for this one also slab weightless. Okay, and it's done. Not the shear wall, so that is still transfer the load, right? This is only to make this diaphragm. Okay, so actually the diaphragm is, you have two ways. Either you don't model the slab and click this entire uh, area and make it as a rigid diaphragm, so that it moves like a one rigid unit, or else to model the slab. And if you model the slab, you can even mesh it and then apply the loads on the slab, or else, as I did, so you already added the loads to the beams, so you only need the mass of the slab only, not the weight, right? So still the load of the slab is not accounted, but only the mass, right? So this mass is need for the dynamic analysis, right? The mod shapes and everything, so we make sure that it is correctly represented, right? So and we can also allocate for the additional mass also, right? So we'll do it later. So you can see, so something special here, the slab is 175, which is fairly higher value, right? So what you can do is you can add a secondary beam, so that your spans will be reduced, and your slab thickness can be slab thickness can be lowered into around 100 and let's say 25. Okay, so if you remove it, so you will be removing 50 millimeters of concrete, right, from the entire slab, so which is approximately 1.25 kilonewtons per meter squared. That will also make a big change in the model. But if you use secondary beams, so you have to cast additional beams, so that is laborious, right? But still, if you use secondary beams, so your moments and everything will be lower, so that your reinforcement also will be lower. Okay, so those advantages and disadvantages are there, right? So I will use this model, right? And I will go to open in this one. Yeah, this one, right? Oh, yeah, not sure I have loaded it. Open slab loaded. So okay, so now you'll see this one, and it is loaded accordingly, right? So unit load 1, I have put these values, right? So everywhere it's here, and unit load 2 also, right? So I have modeled the slabs as well, right? I think I have something mistake here, area sections. So slab 175 modify, yeah, it's done. 175, and slab 200, that is also 200, right? So no, secondary beams, that is secondary beams, you have to be careful, because you need to keep it as here simply supported. That is more advantageous, because if you have something which is connected to this, so when this beam deform, right, when this beam gets a moment, so it will apply a torsion to these beams, right, end beams. So the interior panels is okay, right? So because in this side also it will get defect, the other side also get it, so the torsion will be mostly negligible. But here at the end, so since this beam transfers a moment, right, so that this beam will have a torsion, so it's better to keep it as simply supported, right? Okay, so yeah, we can go with uh, the modeling, right? So I think I defined everything. Load patterns, yeah, it's here for the load combinations, right? So now you can go to load combinations and slab. So you can modify the slab, and you will see. So places where unit load 1 is applicable, I will use 4.2. So that is, I think, 25 into 25 into 1.175, right? Is it right? Or to, yeah, so yeah, if it is density is 24, so it's 0.175 into 24, which means 4.2, and if it is 200, so that is 4.8, right? So slab is there, so that's done. So finishes, okay, so for the finishes, I will use this one, right? Modify. So finishes, I will use 1 and 1 for both, because we usually use cement rendering, which is 0.5 kilonewtons per meter squared, and with with additional, with tiles and everything, okay, you can, it's safe to assume around 0.75, and that's why I use 1, right? So cement rendering is usually I think 20 kilonewtons per meter, so the density is, so that 25 millimeter thickness you will get 0.5 kilonewtons per meter squared. With tiles and everything, it's safe to assume 1 kilonewtons per meter squared, okay? So, and for the services, you will use services 0.5, right? 0.5 and 0.5, but you will see in this lift area, mostly services will be concentrated, so that you need to be aware, right? So that in this middle core area, right, core area, they will have different services, right? Washrooms and the other things, right? So that you can aware, you can be aware, and apply some different unit loadings to compensate that. And for this one, so the partitions, right? For the partitions, I applied 1 kilonewton, so that I will not have any partitions in this area, but the remaining area, so that I will use only for unit load 1, right? So everything's done. So I will use these combinations, right? So I have several combinations. Let me show.
Excuse me, sir. I think you are muted.
Oh, sorry. So can you see this whiteboard?
Yes.
Okay. So so if you are using euro codes, right? So you use dead loads and then live load and wind loads mostly for these tall buildings, right? So this is permanent load. So these two are variable, right? So you know this partial factor of safety is 1.35 and 1.5 for variable, but these two will not act simultaneously. So if one is dominant, the other one has a partial the another factor to because if the live load is leading variable, so it will be 0.5 and this will be multiplied by 5 2. So where this 5 is around 0.5, right? So if wind is the leading variable, so it will be there and this will be multiplied by 5.1 where this is 0.7, right? So that this will be equally 1.07 and this will be 0.75. So these are your factors, right? So I will take the first combination, right? First combination is the building is just constructed, there is no live load. So you have the dead load and you have the wind load, right? So this is like a cantilever beam, right? So when this load is maximum, right? When this is the wind load, right? So it will create a huge moment, right? So you know WL squared over 2, right? That's the moment it will apply. So similar goes with how you idealize a tall building as a grounded cantilever, right? So when cantilevers are applied, so you will know here you will get in the beam you will get tension here and compression here. Similar in the tall building, you will get tension here and compression here, right? But with this dead loading, that tension will be reduced, but we need to know the maximum tension so that we will use unfactored dead load and factored wind load, right? So we need to see the maximum tension, right? If the to see whether there's a tension occurring here, right? To see whether there sometimes there will be no tension, right? So we'll use that adverse load. So we factor it and we reduces the dead load as much as possible. We need to see the maximum because if we use factored, so this tension will be again decreased, right? So for the second load case, I will use so this load case plus so 1.35 GK plus 1.5 into so where the wind load is still leading WK. So this will give you 1.05 QK, right? So for the third load case, I will use 1.35 GK and 1.5 QK plus 1.5 into 0.5 WK where the live load is leading, right? And fourth load case where there is no wind, right? 1.35 GK plus 1.5 QK. Okay. So these are the four combinations that I'm going to use. So yeah, so that I can go for again modeling. Right. Yeah, I will. So So you have wait a minute, because we use in that model analysis we use 12 EI over L square, so which is what the under the assumption of slabs are infinitely rigid. So you know the reason I taught you, right? So in that case, the real case is actually between fix and pin, right? But that's more computationally expensive, so that it's safe to assume slabs are infinitely rigid. And we make another assumption: axial loads do not contribute to any deformation or change in the stiffness, right? Okay, so in that case we can assume those stiffness values. So you can actually read more about these things, right? So I'm still focusing on this modeling, right? Okay, so yeah, is it clear up to this point? Is it clear? So I can go ahead and make the combinations. Okay, so I think I have already made the combinations. I will use that model and show you how to do it. Show you how to do it, right? So open the model and not sure what this one is. Yeah, I have calculated the wind loads as well. So for the moment, I have applied it. So you have to apply it x direction and all as well as in the y direction also. Wait a minute. So you will see. So wind is yeah, I will show that as well. So hope you can see the whiteboard. And so when you have a building like this, it doesn't matter whether it is the code you are using. So this side is windward side when the wind is acting on this way, right? And this one is the leeward side. So we use only these two direction for the coding, right? Windward, leeward. So codes usually define theta equals 0 and theta equals 90. So they reduce other cases, but you can consider those things in a different combination, something wins something like this. Okay, so for the moment we will use these things. So if you have something like this, you can directly get it. So this is the windward side, this is leeward side. So leeward side you will have the suction, so where it pull the building, and windward side that pushes the building. So I had already calculated the wind load, so later we can calculate the wind load, right? So in the windward side, I can apply as a point load, it's around 70. And for these lower floors, I can apply around 50 kilonewtons, right? So it's not a line load, it's a point load. I'll show the reason. And in the leeward side, you can, the entire distribution is uniform and you can apply 40, around 44 kilonewtons. So I will apply the same loading in the y direction also, y direction windward and y direction leeward. Okay, so go to SAP 2000, right? So go to XY. So I have just applied. So I selected these points, right? You will see it is in the other way, right? So this way you can see I have applied a point load. If you see it, you just need to assign joint loads, forces. So you have to apply it is in y direction. So y direction, you need to apply 44, right? So I have already applied it. I will not apply it again. So the load case should be wind by, okay? Wind by, Okay, here also it's wind Y. For top 15 floors, you will apply a load of 70 kilonewtons, right? And for the bottommost, you will apply 50 kilonewtons, right? So I didn't show you how to extrude the floors, right? So for that, you can go with slab loaded with combos. I think it is still there. You can delete it, right? So you can go to XY. So set 3D view XY, patch 0. So you can select everything, and you need to press. You need to replicate it, right? So you can replicate it. Press Ctrl R. So flow to flow height is 3.6. And I will use it for 14 times. The reason is top bottommost 15 floors have column size of 1000 meters, and topmost 15 has column size of 800 millimeters. So I have already modeled the floor, so I need another 14 only, right? So now it's done. So after the loading also, okay. So if you have the loading, then you can copy loading also to each flow. If you want, you can display it, right? From this one menu, go to frame, display options, load assigns frame, and you will see what is loaded, right? So, and from this flow, I will make a copy of this flow. Okay, so one time, and then for these columns, I will assign frames columns 800. Okay, columns 800, and then copy it further 14 times. Okay, now my model is done, right? So you'll see all the things are there. So it's properly supported. And for this one, I can apply the wind loading. So for the X direction, I can use it 3D view and XY aperture 0. So I can use tire. So make sure sometimes the supports also get selected. Yeah, this is not needed. So you can assign joint loads forces, wind load in X direction. So this is leeward side. So anyway, the load is 44 kilonewtons. That's done. So similar thing you can do with this way. Okay. So if it is XY, right? XY view, right? So you can select this one, and you can assign. Yeah, make sure the support is not selected. Support is not selected. So these has a varying joint load. Okay, so I will apply it later. So I will first apply 50, right? Index. But for the topmost 15, you have to apply a load of how much? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Right. So you can, I think, view, show the selection only, right? So now you can see, but yeah, I need the middle plane, right? So you can go to show all, set 3D view, XZ is 0. So select the building with 1, 2, 3, 4, 5, 6, 7, 8, 9, 13, 14, 15, right? Show the selection only, right? 3D, skip it, so you can quickly select these 15 points and apply 70 and replace the existing load, right? And similar thing, you can do it in Y direction as well. Same wind load I used, so you'll be learning how to calculate the wind loads in the fourth or fifth lecture, right? So so I will use this model. So wind loads applied already and combinations. Yeah. So wind loading has been applied. So if you want, you can display the loads, joints load and wind. You can see the wind loading is there, and yeah, 70 is there, and yeah, the wind loads. It's there 70. Yeah, and then I can see joints, wind by. So that's there. I think I have not applied it here, so I will use it again. 3D view, XY, right? So I can use it. Did I apply? Oh, I think I made a mistake. So this is X direction, right? So here you will have yeah. Here you will have this is the windward side. This is leeward side. Okay. So I will add it again. I have already applied, right? So what about this way? Sign, assign, joint loads, forces wind x. So whatever replace it. So 44 kilonewtons. That's done. So everything's done. So I can display again. Yeah, wind x is there. And wind y also there, right? That's done. So that's correct. So yeah, now I can go with combinations, creating combinations. So I had already these four combinations. So combination one is, so these are ultimate loads and slab live load also modify. So unit load one, live load I will use 2.5, and for unit load 2 I will use 4 kilonewtons per meter square, because that area which can gather a lot of people because of the lift, right? So I have a reason for everything, right? Otherwise don't just like, if you are not certain with some areas which can be loaded it heavily with some vehicle loading and let's say something like a ram, so it's always better to use a load of 5, right? So let's say you have some a classroom, right, where the seats can be removed. So you originally designed it for 2.5. So because at the end of the year people can dance, which will create a static and dynamic load both, so that this 2.5 will be double when they jump and dance, right? So that will be 5 kilonewtons per meter square. That's why they use usually 5 kilonewtons. But there's another case also, I will show you what it is. So combination one is, so dead weight I have added 1.35. I will automatically calculate it. That's the frames, beams, and uh, the shear walls, not the slab, right? Slabs I have used slabs different. So this is the weight of the slab, right? I have added it as a load, but the mass of the slab I have defined in the material. That's the difference, right? So I have the rigid diaphragm so that it will move together as a rigid unit. So here every factor is there. So slab also 1.35, and for wind, so this is wind loading, wind loading dominant, and this factor should be 1, right? So the minimum dead load, you can modify it. Dead load is minimum and wind load is maximum. So you can see the you can see the effect, whether there's a tension occurring on the foundation, right? And the slab one x-axis, now the wind is in particular direction, so it can be in the negative direction as well, right? So everything's 1. And so this is minus 1.5. So wind is in negative direction, right? Same things you can combine for y also. So wind in y direction. So these things should be 1. This is because combination 1. Modify. Right. So it's still linearly add, okay? Wind in y direction is y. So y wind only, right? And the other thing, so I will yeah, will modify it. This one, okay, 1. So this takes a lot of time, right? So wind in y direction, but negative, right? Y, okay. So for the second combination, you have the wind load leading and the secondary as the live load. So you can modify. So you have 1.35, 1.35, wind load 1.5, but why there's a 0.525? Because it was 1.5 into 105, right? So what actually happens is So I told you, like, you have apply live load to each floor, right? So there's no chance that all the slabs are getting loaded with that heavy loading at the same time. So you can reduce the live load factor. So usually if you have floors above 10, right? Floors above 10, you can use a live load reduction factor of around 50%. That's why so the factor was 1.05. So I divided it by half, so that becomes 0.525. So you use for this entire model and entire combination, you use for the live load, whatever the combination, you will multiply it by 0.5, because that's the live load reduction factor for this building. So if you have floors between 5 to 10, so you can reduce live load up to 60%. And if you have three floors, you can reduce 10%. But for 2 and 1, we will not reduce, right? 1 story or 2 story, we will not reduce. So I hope you got the reason. So again, the same thing, it's in the other direction, wind, right? And this one is y direction, right? Everything's linear adding, right? So other direction, wind by, right? Combination 3 is where the live load is dominating. So the factor is 1.5, but you have to reduce by 50%, so that you will use 0.75, right, for the slab live loading. And wind is now partial factor is 1.5. That secondary factor is 0.5, so that is also 0.75, right? So wind in the reverse direction and wind in y direction and wind in y reverse direction, right? So combination 4, there's no wind, so you will use dead load, and live load not 1.5. Now we are reducing by 50%, right? So envelope X, you can modify. Envelope is the takes the critical of everything, right? So combination 1x, 1 reverse direction X, 2x, 2 reverse direction X, 3x. So combination 4 has no direction, but use it. Scale factor is 1, so you have to use not linear but envelope in X direction, and envelope in Y direction as well, right? And then you can go to envelope in both direction, create envelope X and envelope Y, and go to envelope, right? So likewise, you can define the service loads also, right? I'm not going to modify those. So service, everything will be 1, right? Service combination 1, right? But still the live load reduction factor of 0.5 is applicable in the service cases as well. I have not defined those cases here. Live load factor is applicable here, okay? So you can define. So I have already defined the ultimate units. So for service, I will just define. So you have to define those each and every combination. So I'll go with now the model is already done. Yeah, I will use it. So model is already done. You can run it. So run now the model as well. So you will see what's the difference happen, right? Okay, so you can see, so mode 2, so mode 1. Now you can see the first mode is not a twisting one. So our structure is not a twisting one. It is non-twisting. The second mode, but you will see a torsion modes fairly, right? So the third mode is also a translation in y direction. So why does this happen, right? So we arrange the shear wall to get this shear center of this building to the center, so that it becomes, so we can do a calculation for this shear wall arrangement using I values. We will do it later in the structural forms. So that I took the shear center to the center of the building, so that the mode is now it is non-twisting. You remember the last time we created the first mode was a twisting one, right? But the period is fairly large, because if we take 0.1 per flow, it is should be around 0.3. That's okay, 0.3, 0.3. So it will oscillate more time than the that can be reduced. So it is not. So you can display show tables and structure output mass participation ratio. You will see 72% of the mass in x direction. Only for there is around 0.2% of mass participation for that twisting mode. And for the fourth mode, you have 11% of mass participation. We'll see what is fourth mode is. Yeah. So this there's a slight chance to occur something like this, right? There's a very less chance, right? We will see. So the third mode is this. So I have another question, right? So if you see the building like this, right? So this is a beam, right? Okay. So this is a beam. If you have something like this, so this beam is like this. So X, Y. So this is the shorter span. So this is the longer span. So it is usually weaker in this direction, right? Than this direction. But so if I see our building, so this is building X and building Y. So our building should move in the weak direction, right? So it should move in this direction, because ixx is lower than iyy, right? So if you just take a beam like this, so it is hard to move in this direction rather than this direction, right? So you know the reason, right? So ixx and iy, but why is it still moving in x direction first? The reason is you have some fairly strong walls in this direction, which increases that stiffness, right? So this wall will increase the stiffness in xx direction, the perpendicular direction. So we have only smaller walls and smaller 3.6 walls in the yy direction to increase. So this will, right? It's not actually iyy, so you will know the reason later. So in this direction, even though the ixx is low, so these walls are now converting the model in x direction fairly stiffer than the y direction. So that's why the first mode is in this way now, right? You only have 2.5 and 2.5 and 3.6 in about y-axis, right? So that it will not move in y direction because of this reason, stiffer walls, right? But it will move in x direction, right? So I hope you got the reason, right? If not, you can reach me via the phone, so I can explain. So let's see what happens now. This you will see this Fill objects. So you will notice that this beam which connects so this beam which connects the two lifts is it's a coupling beam, but the beam is not a strong beam, so it's a 0.2 into 1. So if you connect it with a strong beam, you can see coupling action, which is both walls will act together as a rigid unit, right? More like a rigid unit, right? So that it will reduce the stresses. We'll do the calculations later, probably in the structural forms. So coupling action, we call it coupling action. So we'll see what happens if you connect it with a strong way. And for example, still I didn't calculate the real mass so that I can define the mass source, because modify the mass source. Oh, sorry, I cannot do it still. So I will define a mass source, modify the mass source, specified load patterns as well, because now I only have the element loading only, right? Elements only, because element means I have added the mass of slabs. So you remember, right? It's weightless but has a mass. So that mass is there, and beams, columns are there. But how about the handrails? Those things, right? Those things are not there. And also the loads from the additional finishes, I didn't take it. Sometimes some people use a line load at the perimeter, right? Uniform line load, okay, at the line UDL at the perimeter to account for finishes, but I didn't still use it. So that I will assume, right, dead load was also there. So for the unit load 1, right, so I will assume for 70% of the finishes will be there, right? 70% of the finishes will be there. And from the so that means 0.7 into 1, right? 0.7 into 1, that is 0.7, right? And for this is for unit load 1, and I will assume 80% of the services also account for this mass. So I need, what I'm doing is I'm calculating the most accurate mass, right? Because you have everything for this mass of the building, right? So you need to correctly calculate it, right? So you will one, so I will use 80% of the mass, so that it 75, okay, 75 or 60%, that's okay. I will take 60% of the services, which is service load is 0.5, 60% is 0.3. So 0.3 plus 0.7 is 1. And then partitions, I will take 70%, right? So that is 1 into point, so partition load is 1 into 70% is 0.7, so that everything becomes 1.7 when you add it, right? And for UL2 also, UL2 you will not see any partitions, but service and finishes will come, so that it will become 0.1, right? Edit. So you define the self masses and additional masses, now load patterns as well. From the loads, you calculate, you get the masses, because you need to define accurate masses which are not modeled, right, into the mass. So we'll go and run it. So what has happened to T? 3.6. Earlier it was 3.3. Can anybody happen? So the fundamental equation is T equals to omega K over M, right? So what we did was we increased M. So theoretically, omega is K over M. So the omega, what happens to omega? Omega decreases, T increases, right? So that's what happened in the model. So you should be able to interpret your knowledge, these results using your knowledge in the structural dynamics, right? So omega is K over M. So we increase the mass. Now we have the most accurate mass of the building, right? We'll assume that, and we increases M, but not the stiffness. So what then happened was, we increases the natural we decrease the omega natural frequency, and T equals 2.5 over omega. So it will increase the period. So it is 3.68 now, right? So we will see what will happen if we use that coupling beam, right? So that frame sections, you can go for that coupling beam. So I will modify it. So I will use a fairly deeper beam, right? Fairly deeper beam. So at coupling, so modify it. So this is not actually, so modify it 1.2, and this is a point, I would say 0.3 with this, okay? So at coupling, so this is the beam which connects this one, right? I think this one. We'll see the sections. We'll see the sections. Not extrude in standard. Going to fill. So you can see the sections, object, element assigns, frame, sections. Display. Yeah, this is at coupling, right? So now I have changed that property, right? So that it is how much at coupling is 1.2 into 0.3, right? So now fairly deeper beam connecting shear walls, so that the structure becomes fairly rigid, right? Stiffness will be high. So you know what should happen in the model, in the period, right? So what has happened actually? So you reduce the natural period of the section. What has happened is, so the structure becomes fairly stiff than the previous. So you will see the fundamental period becomes 3.3, right? So if you need, you can go still start animation. So it will move in this direction still, right? So I think you understand these things, right? So we'll go to results, and we'll stop this animation. So you can calculate each deformation for any lobes and any combination, right? Deform shape, and even the contours, right? UX, UZ, UZ means the bottom, right? Okay. So, and you go to shells, you can see the loadings for any combination or any lobe. right? So the shell elements will be there. So you will see is loading, right? So should be properly connected, and then M11 and M22, those things are there, bending moments, you can calculate it later, right? So go to frames, cables, bending moments, envelope. So yeah, you see the values. So if you click one beam and right click it, so you get the shear and moment of that beam. Okay, so now I need the model the foundation, so I will use this one called I need to see the reactions, right? Tabulated for the envelope, right? So I need to see xy at set 2D view, xy plane at z equals 0. Yeah, so you will see most probably these reactions are larger than 10,000 because of the wind, right? If wind is not there, it will be around something lower than this. So we have, I think the largest one I could see was, yeah, it's around 15,000, 15,000, 15,000. So I can, it's for the modeling, I will use around something around 16,000, right? But for actual modeling, you have to know the values and design the piles accordingly. So for the time being, I will use something around 16,000, right? So for this one, have a foundation, let's say piles. Okay, so these piles, if you consider 600 millimeter piles, can take safely ultimate load of two up to 2,000. So for I'm assuming it's around 17,000. I will use 4 piles of 1,000 millimeters for the modeling and 20 meters, right, to the bedrock. Okay, so designing piles also. So for the spacing between piles, I'll specify 2.5 into pile diameters, but for larger piles, it's preferred to have 3 point diameters, right? So 2.5 diameter means diameter is also 1 meter, so that's 2.5 meters. And for the from the center of the piles towards the outside, you will have the radius and some additional spacing to bend the reinforcement. So that is a minimum is required to 150 millimeters, so that our pile radius is 500 and 100. So that will from the center to the end of the pile cap, we will have 650 millimeters. So because we are bending the reinforcement and fabricate it, right, in the pile cap, you may have seen, right? So the modeling of pile, so this is the pile, so it's on soil, right? So soil can settle and have some stiffness, right? So that stiffness, okay, depends on the depth of the soil, right? The horizontal in x and y direction both, right? You can see only the plane, it's in x direction, so it will come from the towards the plane of the paper, right? So in that's y direction, the paper is in x direction, so both x and y. So these subgrade reactions should be known in order to model this one, right? So we can for this n bearing capacity, we can assume a fact the springs is this equation, factor of safety into 40 into bearing capacity. Okay, so for the springs, right, for the springs, and since we have some bedrock at the end, we don't need to spring at the bottom. We can consider a pin support that it will not settle easily because it's the bedrock, right? So so this is depend on the soil, right? You will see KH is the horizontal subgrade reactions, that's K. So that depends on NH, right? N is one for sandy soils and 1 for normally consolidated soil, right? Over consolidated, it's 0. So if you have sandy soil or normally consolidated soil, N is 1, so which will reduce NH into Z over D. So your D is also diameter 1 pile, right? So that become NH into Z, right? So you know the Z that is in the model, so you only need to calculate NH. So that is area into gamma over 1.35, the density of the soil, right? So A is in the range of this, right? If the loose sand, A is in the range of 100 to 300, medium, medium sand, right? So it's 300 to 1000, then it's in this range. So gamma H, right, for moist sand, NH for moist sand can be in the range of by calculating using this, right? Gamma, if gamma is 16.5, it's safe to assume 5000 for both these cases, right? Okay, so the range is given from this, right? So NH can be calculated. So when you know NH, right? So NH is directly given. NH, if you know the NH, that is NH times Z, right? So I will use NH is 5000, okay, for the modeling, and Z is, so this area is the projected area of the pile. So KH is actually area, right? So this because this horizontal subgrade reaction is, this K is units are kilonewtons per meter squared, that you need to convert it to kilonewtons per meter into stiffness, right? So that you need to project it from the area. So that area is the diameter and the depth, right? So that is also 1 meter. You will take 1 meter interval. So that is 1 meter squared. Diameter is 1 meter. So we will divide the pile into 1 meter sections, and we'll use 5000, that becomes 5000 into Z. So this diameter will be anyway cancelled, even if it is not 1 with this area, right? You don't need to worry. So I will assume 5000 into Z, right? So I will draw one pile, okay? So go to XY. So go to XY, right? Right. So here I'm going to remove the support, right? In order to do that, so I will first draw some beams to draw the pile caps, right? Replicate it, dy direction -6. Okay. Polar dx in 7.5. Why I'm doing this is to draw the pile cap, okay? So you remember pile between center to center, you had 2.5, right? 2.5 meters. So that means you have to replicate it in 1.25, which is 2.5 into 0.5 meters, right? Extension, and this is also again in y direction, right? So this is again in direction. This is also in y direction. So that's done. And from the center of the pile, you have 650, right? So that is 0.65 meters. Okay. And yes, that's done. This also 0.65 in x direction. Duplicate it. Yeah. Now right. So these are the pile centers, right? So still I have not divided it. So you have to divide these elements from where places where intersects. Divide frames, go to, and yeah, now it's done. So what you can do is, so these are the pile centers. So you can extrude the pile. So in order to do that, I need to define a section for the pile, right? So define section properties, frame sections. I will add a new property, concrete, circular one. The pile is 1 meter, pile 1000, right? So it's in concrete. That's done, right? So I will extrude points to frame. So that's dz in minus 20 one time. The section is, so you can add the section here. Where's the pile? Yeah. So you will see the piles there, right? So now you can add the bedrock condition, you can give by pin condition, right? Okay. So and go to XY. You don't need this support now. You can remove the support, and you can draw the pile caps now, right? Draw rectangular area. That's I didn't go with the pile cap, right? Define an area section, wall, add a copy of section, pile cap. Pile cap will be around 1.8. 1.8 and shell peak. So draw pile cap. So here are the pile centers, right? So this is the place where I extruded the pile. So I'm not satisfied with the mesh. So I will divide it, edit areas, divide areas, number of 2. So that's divided. So this will also be divided in the x direction. Divide areas in this direction, but not in the other direction. This should be divided in the y direction. 2, 1. That's done. Yeah, now I have some good mesh, I think so. So I can edit this line. Again, I can join these frames, right? Right. And delete it. So now my pile cap is there, right? So it's here. So this now the model is complex and it's not completed yet. So I have only couple of minutes, 10 minutes, right? So the file is done. So what you can do is, so you can go to XZ plane. Yeah, you can divide this frame into 20 parts. Because that's how I'm going to add that now up to this side. So you see this point. So horizontal subgrade reaction you can add with this one. Joint springs. So the subgrade reaction is translation. So you 5000 is it, right? For the 1 meter, it is 5000 in translation first direction and translation second direction. That's done. Yes. Right. So from the second meter, it is you have to carefully do it. Springs. This is 5000 into Z. Now Z is 2 meters from the pile cap. It is 10,000. Right. Now it's done. Right. Likewise, you have to go up to this point, right? That will become around maybe 200,000 or I don't know. You have to calculate and add it. And then you have to copy this. You can copy the same file to the place where it repeat, right? For example, if the pile is repeating here and here, you can replicate it. This is in X direction minus 7.5. That is 4 times, right? Yeah, 4 times. That's done. This is replicating in Y direction. It's 6, 4 times. That's done. For something like this, you have a combined pile cap, right? You have seen in the lift area, there's a huge lift core, right? So the entire area is a large pile cap, right? So something like that, you can do it, right? So when you analyze it, so you need to get rid of these supports. So it's still the structure is not stable. I'll show you why in the next week. Joints, restraints, I don't have any supports here. So you can, it's safe to analyze. So you can get the bending moments due to the piles, right? Right. I think these shells has not been connected properly. That's a reason. I should check it. So you will see this one and carefully draw it to the others, right? To the other locations as well. And when you do it, you can go and analyze it, right? Very carefully. Yeah, the piles have not been copied. That's the reason. So I think I did not, I just only copied the pile caps. That's the reason. So you can copy these, and later we will see what happens with the last one. So something combined pile. So there, I think pile is here, and for this area, you can have a large combined pile cap and have piles at some locations for the modeling, right? And here, right? Maybe it's 12 piles can be there, right? Here also, right? It's a combined pile cap. So the same thing. So you know how to get the capacity of the pile. And there's only some few stability check to be done, which can be done later. Yeah. Let's say if you connect it, final thing is you need to connect it using a beam. So I will use this at coupling beam, right? So you need to connect these pile caps, because at the ground those are everything connected. So what is in the site, you have to give those condition to the numerical model, right? So use coupling beam, I think this one. So sections can be different. I just use this coupling beam to connect it, right? Like this, you have to connect each in this line, this line, this line along this grid, right? So it doesn't need to be the center. It doesn't need to be the center, right? So if you have some pile cap, let's say here, so we have to connect it then to this location, right? So likewise, you have to connect it in the other direction as well. Say, let's say from the pile cap, if the end of pile cap, let's assume the end of pile cap is this edge, right? That's why I connected here. So whatever that should be. And one last check is after you draw those things, right? Sorry. So still now we have removed the supports, but in the actual model we have soil here everywhere. So that structure cannot move, but this structure is unstable in that plane. So we have to make it stable. So what we can do is we can add a add imaginary beam from this pile cap to here and here and here, and from here 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 and you have to fix it at this end location, restraint, fix it. So now, so you have to do it in the all, for all pie cap, like this, like this, like this, like this, like this, here and here and here and here. Okay. So finally, and you have to, so these beams are moment released frames, right? So these are imaginary beams anyway. So you can restraints actually frame release moment 3 at each end. So there are no moments at each end, right? So that will act as, so that will restrain the model, right? That will restrain the model in this plane. Then finally will be stable, and pile foundation is also completed when you add spring at each meter, so that you can complete the model in this way. And already these pile caps should be connected in X and Y direction, right? Similar to this, right? From pile cap to pile cap, if there's a combined pile cap, right? And here to here also, here to here. So then the structure is fully completed. Okay, we'll see the next time. So modeling is completely done. pile, including the pile foundation also, and the wind load, everything's there. So you will see when the wind comes, sometimes there will be piles in tension, right? Sometimes there will be piles in compression. So you can model this one and analyze the results. Yeah.